Hey, happy Wednesday. Happy last day of class. Happy everything. Today's Wednesday. It's the last day of school. Make sure I don't run over the dog while I move around. Let's see. Trying to think if I have anything exciting to share. Not really. It's the last day of classes. So it's my most favorite day in class, but it's always a fun day when we work a few problems, talk about life. I feel like I unleash you as grown-up scientists, and today we're all at home, hoping that we can go outside soon. So let's see. There was some other, I don't want to call them excitements. I'll do that. Announcements, end of semester things, all of the exciting things. If you have questions, you can go ahead and drop them in the box. I will start with Michael's question and go from there. Today we will talk about chapter 10. I have a couple of example problems that if we don't get to, I will post on Canvas today. Something else. I am ready to go back to school. It turns out that I've always wondered, would I be good working from home? No, I don't want to. I want to go to work. I want to teach in front of people. This whiteboard, not quite big enough. If I was going to do this permanently, I would turn that whole wall into a whiteboard and I would just write on the wall. But that's a lot in the house. So we'll not do that today. Let's see. It says it's 3:03. Okay, so we'll start with general announcements. Then we'll answer all the questions in the tick box. Then I'm sure we'll go through it again. So we'll start with the quip, so if you miss any of this information or want it in a written form, on Canvas in the second module, I think it's called lecture announcements, the slides that I used to show at the beginning of class. Today's has all kinds of good stuff in there. So today's quip is over, oh my gosh. Oh, right. Ideal gas law. So it's very similar to the stuff that we did on Monday. PV equals nRT, P1V1 equals P2V2. There are some equations in there. So this one is, it's the first one that we did at home where it'll have a blank for you to write your answer. You don't have to show work. You don't have to upload work. You have 10 minutes. I think the first one that was math related, there were a couple of people who were like, so I wasn't ready when I hit go. So it's just a regular quiz. It unlocks at 4:15. I think it's already published, but not available. At 4:15, I will double check on that. So today's quip is over the ideal gas law, so PV equals nRT, and those kind of permutations. So it opens at 4:15. It closes at 11:59. The other thing of note about the quizzes is what you should have seen in your grade book is, what was I going to tell you about that? For the quips, the old quizzes have become practice quizzes. I am trying to get Canvas to tell you what your actual grade is, not what Canvas thinks your grade is. So that has already been done. I'm hoping to have this quip graded and migrated by Sunday. And then you can go in and see about what's left, point-wise. Alex, you have objectives due Friday. Those are for chapter 10. I think there's 9 of those, give or take. Those are due on Friday. But once you complete those, it becomes open pie. And if you'd like to earn 100 points for Alex, for the pie points, you need to have completed 100% of your pie. The bar at the top needs to be either blue or dark blue or light blue. So there is not a knowledge check for this week. I took that away. You guys have been kind of busy, and instead of remaking, you go back and redo objectives since our finals on Monday. We'll talk about that. Office hours. So I have office hours tonight at 5:45. Megan has an SI tomorrow. She will be holding final review this weekend. Details from her are forthcoming. On Sunday from 3 to 4:30, I will be available on Zoom, the usual place, the usual time. Well, not the usual time, the usual place. I will send an announcement in my Friday announcement with a direct link, so you can open that and click on it. And then Monday, 1 to 2:30. So I will answer these questions, and then I will go back and then we'll talk about the final. So Thomas says there's 8 objectives due on Friday. So you have 8 of those. I answered Allie's question about the QUIP topic, and I will be reposting the worksheet keys. They will go up probably this weekend sometime. Same with the chapter 10. Okay, the point scale for this question. Caitlin's question is, if you have the 70 QUIP points, then that is the highest you can go, correct? That is true. If you get a 70 out of 70, and there are lots of people with 70s, you do not have to take today's QUIP. You totally can. You can still earn points for that. They just will not count towards the total for QUIP. So if you already have a 70, you're good to go. If that answers your question. So Michael asked our first question, which I know it feels like I'm avoiding it. I'm not. It's just the longest one. Is about the grading, the point system for grading. So in this class, the way it works is if you achieve, and let me actually pull up nope. Let me look at the actual syllabus so that when I give numbers, you guys aren't like, wait a minute, that's not right. So what the letter grades that you see on Canvas are what you currently have. So in my class, if you get 1,020 points, you will get an A. So that also correlates to 85% and above. So one question I've gotten several times is, well, what about, so if you have a 65 in my class, that is a C+. Maybe in a different class, the 65 is an A. In a different class, that might be an F. In a different class, that could be any number of letter grades. On your transcript, what you will see and what anyone else will see are the letter grades. So in my class, in order to pass, to get a satisfactory, you need 58% of the points, which is 696. So if you've gotten that many number of points, you technically don't have to do anything else. If you're okay with getting a C or a satisfactory, and you opted into that system. So what you have left to complete in my course, we have a QUIP today, which is worth 10 points towards your QUIP total. We have the Alex Pie and the Alex On Time, which is 200 points. And then we have a final, which is 300 points. So there are still what I would call a lot of points left on the table. If you realize that you have not turned in Alex in weeks and weeks and weeks, I would recommend that you try to get 100 points on the Pie points. You may not get the on-time points, but the other points will be helpful. Michael, if that's not what you're asking about the point system, go ahead and drop another comment. Did you say the grade on Canvas? It should. Yes, I did say, Isvari, that the Canvas it should be updated to reflect the actual score today. I will double check. So 2 questions. So Michael asked, can you get a B-? No, the lowest B you can get is a B. You can earn a B+. And so I only offer A, B+, B, C+, C. It turns out that I don't really care for the minuses. So if you will either get a C+ or a B. So Sam asks how many points to get an A. 1,020. For a B, you need 840 points. Let me write down. I will, on my Friday announcement, 2045, I will add grade point. Any other questions? And then we'll talk about the final, because I feel like if you were coming, you're here, or anything else. And if something percolates to you, feel free to drop it in the box. I will go ahead and answer that when we get to it. Okay, next. Katie, that might be normal. Oh, so Katie's saying, is your grade only out of 700 points? So the reason for that, I think everyone should be out of 700, is because the 500 points, for the Alex for 200 and the 300 final aren't there. You get 100 on Alex if you have an 85%. So the turn it in has to do with how many times you did not turn in your objectives on time. So you have to have turned in 85% of them on time, but you cannot get 100 if you've only completed 85% of your pie. That is true. Sam makes a good point. If you want to test out what you need, you can do the what if button on Canvas. Isvari, I'm going to say yes, that you can see your score in Alex. However, I would like to state with this caveat, kind of. I've never actually seen a student gradebook. So what I see when I look at what I think is your gradebook is it tells you what your percentage is on, it gives you like a final grade. So you can do some math to figure out so your pie is pretty easy. That'll be on the front page. The on time, there are two ways to do it. What I would do is look at your gradebook and see which ones are a 0, because that means you didn't turn them in. And so the gradebook on Canvas is a little bit weird. If you have questions, you can send me an email or stop in office hours, and I am more than happy to calculate that for you. 10 a.m. on Tuesday. So you have a smaller window. If you have a job and you cannot take it on Monday night, please send me an email. You will get more time. You can see it's the score under objective. You will get 2 hours. So you'll get an extra 10 minutes. So it'll be 120 minutes. If you have extended time, I will set up all of that as well. You must submit the short answers within 10 minutes of completing the Canvas portion. So, yeah. The exam is on Monday. It opens at 3. It closes Tuesday at 10 a.m. It will be 2 hours long. You will have to submit these short answers. If you have extended time, that all goes through the DRC, and that paperwork is sent to me through Clockwork. So you need to just send an email if you need that. I mean, I know who has had accommodations in the past. So if you have them, you will get them. That's what that's about. So you have to submit your short answers within 10 minutes. If you do not upload the right file types, or you do not upload files, it will not be graded. It will be multiple choice, fill in the blank, and short answers. Michael asked how many questions. I have no idea. I haven't started writing it. It will be longer. You should expect it's 100 points longer than exam 3 and roughly a third more time. So it will be about a third more longer. If you have accommodations from the DRC, then I should already know about that. So you should set up an appointment. I sit at this desk all day long, all day. If you have needs, if there are things that are not getting done, please send me an email. I am more than happy to help. It will be open book, open notes. To be very clear, it is not open Chegg. It is not Open friends, we know when you cheat, I'll know you will get a 0 and some other naughty notes will happen. Aaron, it is going to be open notes. That means it will be hard. I don't know how many questions it is. All of that information will be in the announcement for that. It's cumulative. So right now it looks like somewhere between 15 to 20% new material. And the remaining material is 80 to 85% of the exam. So my suggestion would be to chunk it into exam 1 will be roughly a third, exam 2 will be roughly a third, exam 3 will be roughly a third. I really like multi-concept problems, so you should expect to see chapter 1 material, chapter 3, 5, and 9 mixed together. I know that there is an SI review session this weekend. Megan's going to send you some email. My suggestion is to hop into those. It will be cumulative. It is open notes. It will be a lot like the previous exams. So on Canvas, does it matter if we type the element name or does it need to be the symbol? So if you write the word sodium and I wrote the word sodium and somehow you spelled it differently than I did, it will mark it wrong if it doesn't match the key. So if you go into your Canvas exam 3 with the auto grade, what you'll see is on some of them, it will say incorrect, but you'll have gotten a 4 out of 4. Because I go back and look and say like, okay, all of these are right. All of these are right. So on Canvas, it doesn't matter. It will tell you if it's asking for the element name or the symbol or something like that. But otherwise, don't fret about it. I will accept both. And if Canvas doesn't, I fix that in the end. Other questions about the final, about anything else? ISQs are due on Friday, so if you guys want to fill those out, you can do that this week. The Google survey is also running around if you guys want to look at that. I will send my Friday announcement with as many details about the final, including when it opens and how long you have and all of that information. Katie, it does open Monday at 3. So any other questions? Class would have been 110 minutes, so you will get 120 minutes. So I will give you 10 extra minutes, mostly because Canvas is kind of trippy. You're fine. Oh, Lily. Hey, come here. Yes, you can see Lily. Come here. Come here. Yeah. Yeah, they wanted to see you today. That's right. Yeah. She misses you guys. But I'm going to be honest, my dog has never been happier because every day Mom stays home. This is her life. So, all right, where do you want to sit? Okay, so today, I wish I'd had this idea like 9 million years ago, but I'm going to try, and I don't know if this will work, but I thought one thing we could do is I'm going to attempt, and so to copy and paste the questions into the comment box in case you don't have the slides up. Because we're going to start on slide 18. And so, okay. It will not fit in one because it's like an old school text message. So today we're going to start with this example. It says, to negative 21 degrees Celsius, calculate the volume of the balloon at its final altitude. So There's markers over here. So in this question, oh, there's a better way to do that. Our inflated balloon, we're provided a lot of information. So I think one thing that we kind of want to think about is how do we categorize that? So I like to think about, we have sea level, P, B, T, and then we have in the air, P, B, T. So the reason I categorize it this way is so that when we start assigning stuff, we can figure out where it goes, because we want to use this equation. P1, B1 over T1 equals P2, T2, B2. So I'm going to arbitrarily determine the sea level is number 1 and the air is 2. I just did that for no reason other than this was on top. So when we think about the volume at sea level, we know that it is 6 liters. We know that the pressure is 1 atmosphere. And the temperature is 22 degrees plus 273 gives us 295 Kelvin. So now we want to think about what's happening in, as it goes up. So now we know that the pressure is 0.45 atmospheres. It asks us what is the volume, so we don't know yet. And our temperature is negative 21 plus 273, which gives us 252 Kelvin. So once we assign all of this, it becomes a little bit more mathy. So now we have all of these constants. Whether you decide to rearrange these with numbers or without is the same. You can do it either way you like. So when we rearrange the equation, we get that B2 is equal to P1, B1, T1 divided by P2 over T2. Algebraically, we can flip these to where we get P1, V1, T2 divided by T1 over P2. So this is all algebra. You don't need to really think about that, but let's start plugging in our numbers. So when we do that, we get that 1 atmosphere multiplied by 6.0 liters multiplied by T2, which is 252 Kelvin, divided by our P2, which is 0.45 atmospheres, and T1, which is 295 Kelvin. From here, we can plug this into our calculator, which we get 11 liters. Yeah, I would. I think I stole this question out of someone else's notes, and they didn't. So we should have 0.15 here and 0.15 here and on all of these. Other questions about this example? Oh yeah, let me move my face out of the way. So, information, but most gases are not quite the homogeneous mixture that we know about. So one thing yes, so as Vari asked, basically the best plan is to write out everything we have, like plug and play. That's how I approach these problems. This is also what I recommend for chapter 5. So anytime it gives you a lot of information, I would write it all. Once you have that, then you can go in and just plug everything in and not necessarily pop out the answer, but you should be able to get an answer. Good questions. So significant figures come out of the problem. So the new answers need to be paired back to that number of sig figs. So in the question we were asked, all of the numbers provided had 2 significant figures. So our answer needs to also have 2 significant figures as well. So when we think about gases, the thing we want to kind of think about is what happens when they don't make a mixture that looks like the mixtures we know, right? So some things separate out, and some gases are heavier and lighter. So we know that CO2 is heavy. We know that we can see that in fires and other places. But we know that helium is lighter, and so the reason we know that is because helium balloons float. So we can always kind of like, okay, well, that's true. So if helium's in a mixture, it's not like if this room is full of like a little bit of helium, I'm not going to start floating. Wouldn't that be fun? But what we can see is that that's how that usually works. So if we look at slide 21, we can start to use the density of air. Now, density of air is a lot like density of liquids or solids. It's mass per volume. So we can start to use this equation. Where density equals mass over volume. And so when we think about air, we can do the number of moles multiplied by the molar mass divided by the volume. So N equals moles. Fancy scripty N is the molar mass. And V is going to be the volume. So we should end up with something that looks a little bit more like grams per mole. No, grams per liter. Excuse me. So if we have the density of mass per volume, the number of moles multiplied by the molar mass, which is grams per mole, moles cancel out, so we'll end up with grams per volume, or in volume in liter. So we can start to calculate information using the density. So the density of a gas is equal to the pressure times the molar mass over RT. So the density of a gas, which is N divided by V, the molar mass, is just a different rearrangement of the equation. And so we can start to think about that. And so the density of a gas depends on lots of different things, but we can use that information to calculate stuff about equations. So next, we're going to do the example on slide 22. I don't actually know if this is helping, but we're rolling with it today. So to give you guys the problems. I wish I thought about this earlier. Whoops. So today we want to calculate what is the density of carbon tetrachloride, so CCl4 vapor at 714 torr and 125 degrees Celsius. So we're going to use this equation, and we're going to plug in numbers to calculate the density of our gas from this equation. So the density of a gas is equal to the pressure times the molecular weight divided by R times T. So when we think about this, we can just start to kind of like a PV equals an RT question, plug in information. And so we know that the pressure is 714 torr. The molecular weight, we're going to come back to that, R and T. T is 125 degrees Celsius plus 273.15 Kelvin. And so in this case, it's going to be 398.15 Kelvin. So there are two different ways that we can solve for R. We can use the R value with torr in it or the R value with atmospheres. Either one will be fine. So in this case, the R value that I'm going to choose is the 0.08206 liters, atmospheres, moles. So 714 torr divided by 760 torr and 1 mole is going to give us 0.939 atmospheres. So now we've determined 3 of the 4 numbers that we need. So the last one is the molecular weight. Now, you might be thinking to yourself, is 12.01 plus 4 times the molar mass of chlorine. Hold on, let me get out my periodic table. And the molar mass of chlorine is 35.45. And so we should get the molar mass of 153.81 grams per mole. So from here, we can plug this into our equation. So we have a pressure of 0.939 atmospheres times the molecular weight of 153.81 grams per mole divided by R, which is 0.08206 liters, atmospheres, moles, Kelvin. Multiplied here by the temperature, which is 398.15 Kelvin. Now we can plug all of this into our calculator and we should get out 4.42 grams per liter. So that sounded real aggressive. What questions do we have about this question? So I went from torr to atmosphere, which I'll write down here. So 714 torr. See this? Yeah. And then I used dimensional analysis to determine that 760 torr are in 1 atmosphere. So this ordinarily in person would have been provided on your equation sheet. It will be provided on the equation sheet for the exam. I have yet to figure out how I'm going to get you the equation sheet. So this is not something you need to memorize. This is just the unit conversion from torr to atmosphere using the 760 torr to 1 atmosphere conversion. Oh, I did not see that. I didn't realize that was your question. Sorry about that. So it is my recommendation that you always show the units. I can see that, Katie. So my suggestion would be to show the units. You don't have to show the units. You've never had to. It does make it easier. And it's easier for me to give you partial credit if you show the units. But you do not have to show units under any circumstance. So I hope that answers your question. Other questions about this? Equation. So we can use the balanced chemical equation. So you could kind of imagine things that I might like are examples where we have to take information from chapter 3 and roll it into chapter 10. So I like a multi-concept problem where we ask about something that involves both. This is the right way to say this. Chapter 3, Chapter 6, and Chapter 10. So that's what I like. And so we can really do that easily with PV equals nRT. So the next question is about automobile airbags. So I will copy and paste this after I read it. On slide 24, there's an example, and it says, automobile airbags are inflated by nitrogen gas generated by the rapid decomposition of sodium azide, NaN3. And then it gives you a balanced equation, which I'll write up here in a minute. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at 1.15 atmosphere at 26 degrees Celsius, how many grams of sodium azide must be decomposed? All right. So in the box right over here is the question, in case you don't have the slides with you. I don't actually know if this is being helpful, but it felt helpful today. So yeah. I will go ahead and write up our balanced chemical equation while you guys start working on it. So 2 Na and 3 solid decomposes, right? So decomposition reactions are where one thing breaks into its parts into 2 Na solid plus 3 N2 gas. Ooh, I'm good. I'm sorry, it just occurred to me today, of course, on the last day of class. So in this equation, you have a balanced chemical equation. We would know if it was words that you would had known. So sodium azide, I would not expect you to know the decomposition of this without lots of extra help. So in this case, if we have a balanced chemical equation, the question is, what do we do now? So we know that what the information tells us is we have an airbag with a volume of 36 liters. We have a pressure of 1.15 atmosphere. And we know that the temperature is equal to 26 degrees Celsius. And so plus 273 gives us 299.15 Kelvin. So now we can figure out N, and N would be the number of moles of nitrogen gas. So N equals PV over RT. If we plug this into our calculator, where we would write out 1.15 atmospheres times 36 liters divided by 0.08206 liters atmospheres mole Kelvin, multiplied by our temperature of 299.15 Kelvin. So when you plug this in, we get 1.69 moles of N2. So it feels like we should be done. We've done math, we've answered a question, but when we look back at the question, it asks how many grams of sodium azide must be decomposed. Well, this is how many moles of nitrogen are in the airbag. So what we need to do is to go back and then go forward. That didn't make any sense. We want to use this information and the balanced chemical equation using the stoichiometric ratios. I know, it's back again, in order to calculate the grams of sodium azide. So this, I tried to pick for chapter 10 any problem that's going to pull from the past. You should be like, oh God, I remember that, okay? So if you wanted to do that, which you do, we're going to take our 1.69 moles of N2. Then we're going to use the stoichiometric ratio the big numbers up front. So we're going to have 3 moles of N2 are equivalent to 2 moles of NaN3. Then in 1 mole of NaN3, it's equal to 65.02 grams of Na. We'll just leave it like that because I ran out of space. So when we plug this into our calculator, you should get 73 T to solve for the number of moles. Then what it really asks for is what was the starting material. So then we're going to convert back using the stoichiometric ratio, big numbers at the front of an equation. And then we can use the molecular weight per 1 mole to give us the number of grams of sodium azide that would be decomposed in our airbag. Do you guys have any questions? So the 65.02 is the molecular weight of sun, I think. Yes, so it's the molar mass. Good questions. So for the next 15-ish, maybe a little bit more minutes, we're going to talk about the other part of PV equals nRT that's important. So we're going to take a break from plugging and chugging and start to think about partial pressures and gas mixtures. So we know that there is a gas mixture, and we know that inside the vessel, they're going to interact with one another. And so the question is, if the gas is often a mixture, the total pressure is equal to the sum of all pressures. So if I'm writing, it's okay. We're on slide 26 if you're looking at the slides. So the total pressure is equal to the sum of all the pressures. So partial pressure is a lot like cookies. Yeah, I talk about cookies way too much, but it's good. So cookies, if I give you a plate of cookies, maybe there's 5 varieties or 10, but the total number of cookies is literally just the sum of all the cookies. So total pressure is equivalent to all of the pressures. So P total equals P1 plus P2 plus P3 all the way up. Now we know that P1 is equal to N1 RT over V. So what this says is that for each of these different gases, we could calculate them using PV equals nRT. So N1, which is the moles of that gas, R times T times V. Now you'll note that I didn't use T1, V1 because they're all in the same bucket. So they're all at the same temperature and they're all at the same volume. So we could think about determining P total like this. So P times RT over V. So the way we can do this here is because if you were to write out all of these for all of the different ones, we could group the like terms together. And because R and T and V are the same for all of these different gases, we can determine that the total pressure is equal to the total number of moles multiplied by R times T divided by the volume. This is dependent upon the fact that your partial pressure is contained within the same vessel. So we have an example on slide 27. I will read it, post it, solve it. So a mixture of 6 grams of oxygen gas and 9 grams of methane gas is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure and what is the total pressure? So the example we are working is, so we have this mixture of 6 grams of oxygen gas and 9 grams of methane gas. It's placed in a 15-liter vessel at 0 degrees Celsius. So what is the partial pressure and what is the total pressure? So we're going to start by determining the moles, then the pressures, then the P total. Let's see if this marker is darker. It's a negative Ghost Rider. Hold on. I have another marker on my desk, and then I have one more. Yeah, I think there was a good one on the desk. So the first thing we want to do is to determine the number of moles for each gas. So for O2 and then CH4, N is going to be equal to our 6.00 grams of O2 using the molecular weight. So there are 32.00 grams in 1 mole of O2. And that gives us that there is 0.188 moles of O2. So we're just using the molecular weight. This is a pretty standard conversion. So next we're going to do the same thing for CH4. 9.00 grams of CH4. And there are 16.00 grams in 1 mole. Yeah. 16.05 grams. And that gives us that there is 0.563 moles of CH4. So could you combine them to do the math? Sam, are you asking if I could add 6 plus 9 and get 15 and divide that by this value? If that is what you're asking, the answer is no. So we can't add grams, but you could add the total number of moles. So you can combine moles, but not grams. So we can't combine grams because it's a relative measure. If you asked how many cookies I ate, and I ate 1 cookie that was this big, that's relative. So like if it was a huge cookie or a small cookie, it doesn't matter if I only ate 1 cookie. It matters in that way. So you can't do that. Good question though. Right now, you could determine the pressure total by adding these 2 values and solving PRT, PV equals nRT. In this case, and then we'll add the 2 pressures together at the end. So from here, we're going to add 0.563 moles over, run out of space, 15.0 liters times 273.15. So the pressure of oxygen is going to be 0.281 atmospheres. And so I just plugged all of this in. Minus the R value, 0.08206 liters atmospheres. Mole. Done. So we're going to do the same thing down here using the value here. I did that because I got confused. Sorry, good catch. So this should be 0.188, which will give you this for P of O2. So for the pressure of CH4, it would be this using those numbers, which gives you 0.841 atmospheres. So now we have the partial pressure of each gas, and then it asks for the total pressure, which P total is relatively simple to acquire. It's just the total of that. So P total equals 0.281 plus 0.841, which gives us 1.122 atmospheres, which I believe has one too many significant figures, so we should only have 3. And so this should turn into 1.12 atmospheres. Right? Yeah. So do we have any, just enough so you can see it. So in this case, in order to solve this question, we just needed to determine the moles and the pressures of both, and then we added our pressures together. 1.12 is the total pressure, and these two are the partial pressures. So partial pressure basically just asks what pressure comes from the oxygen. And so that's related to the number of moles of oxygen as well as here. You could have also solved, which will require more space that I don't have on this board. It wouldn't have given us the partial pressure. We've done the following. I'm going to write kind of small, mostly so I don't have to erase this yet. So we could have also determined P total is equal to the 0.188 plus 0.563 273.15 times R over the volume of 15.0 liters. This, if you did this equation, would have also given you this value. So you can solve it either way. The question is, how would you get at the partial pressures for each of these? So in a shock to none of us at this point in the semester, I'm going to show you an easier way to determine the partial pressures. So if we look at slide 28, and then we're going to go through some of these other ones. So partial pressure, each gas behaves independently and they all interact. So the partial pressures, okay, apparently I wanted to use 100 slides when 2 would do. So partial pressures and mole fractions. I'm going to go ahead and erase the board though. So partial pressures are the pressure that any gas exerts on the system. So we know that P total, the partial pressure, or a percentage of that, so P1 divided by P total equals the partial pressure. So it's basically the partial pressure is a fancy chemist's way of saying what percent of the pressure, what portion of the pressure goes towards any one element. So if we know that P1 over P total gives you the partial pressure. So we can rearrange this to say N1 over RTB divided by N total RTV. When we see like things on both sides, we are on 29. So here's what's happened. Apparently 28, 29, and 30 and 31 really should just be one slide. So in this moment, exactly, I'm writing on things from 29. In just a second, we're gonna move to slide 30, but I'll try to tell you guys when it happens. It's okay. N total is a cool thing that makes a little bit more sense, something called the mole fraction. So N1 over try to go right down here. N1, yeah, y'all can see that. N total is equal to chi, which is otherwise known as the mole fraction. So mole fraction is kind of like asking what fraction of the moles correspond to any given value. So in this case, N1 divided by N total would give you a number. If you wanted to know percentage-wise, you would multiply that number by 100. In this case, we're going to leave it as a fraction, so it should be less than 1. And the mole fraction is the percent of the total moles that any given gas is. So now we're going to move to slide 31. And so we know that, so P1, if we rearrange this equation to solve for the partial pressure, P1 equals chi1 times P total, where the mole fraction multiplied by the total pressure gives you the partial pressure. So instead of using a variety of P1, PV equals nRT or P1 V1 equals P2 V2 or anything else, we can calculate the partial pressure of any given gas. So on the bottom of slide 31, we have a question. And it asks, blink. It says, if the mole fraction of nitrogen in air is 0.78 and the barometric pressure is 760 torr, what is the partial pressure of nitrogen gas? So in this case, partial pressures gave a mole fraction, so that's good. So now we can use this value or this equation to determine what the partial pressure is of nitrogen gas. So the mole fraction, let's talk about this question, then I'll answer your question as well. I see you coming. So if you were provided the mole fraction like we are in this question, you would get, it would be 0.78 times 760 torr gives you 590 torr. So if you have the mole fraction and the total pressure, ooh, Allie, hey, how many significant figures do you need? So Allie got 593, which is what you get if you plug that in. But in the question, you can only have 2 significant figures. So we would round down to 590. It's a good question. Great question. So Isvari asked, how would you find the mole fraction if it wasn't given? So the moles of N2 divided by 2, there have to be, you would be given information in the problem. Yes. So chi1 is N1 divided by N total, and that's called the mole fraction. So a mole fraction is the fraction, well, we'll just call it the percent of the that one gas is. Okay. So it's okay. I'm sorry it's buffering today. #life. So Chi1 is N1 divided by N total, which is the mole fraction. So a mole fraction is the percent of the total moles that one gas is. So if you had, let's do this in an easy way. The mole fraction, let's think about cookies. So if you have 20 cookies total, and 8 of them are Oreos, the mole fraction of your cookies that are Oreos is 8 divided by 20, which would be 40.4. So the mole fraction is just what percent of the total moles. In this, oh, so Katie asked, why did you include a 1? So we need a way to designate what we're asking about. So mole fraction is per everything we have. So if I1 is one of the gases, and it assumes that there's more than one gas in the vessel. So we have another, oh wait. So Sam asked a random, but could we do scientific notation for sig figs? Like instead of that? Yes, so Sam, it is totally correct for you to do 5.9 times 10 to the second instead of 590. I will always accept both. Alex will only select some. So we have one more question. You can ask as many questions, and I will stay a little late today to try to answer all of them. But let's look at another partial pressure question. So hold on. Trying to get my question in here. How many? Coming in a lot of different pieces. Oh, Allie, I'm sorry. Yes, you can leave it in the units you're given. You don't have to change it to atmospheres unless I ask. Alex will do that a lot. It'll give it to you in one and move to something else. I'm sorry, I missed your question. But you are correct. You can always stay in the units you're given. So in this question, this is a little bit more, not in depth, but a little different. So a study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 0.15 mole percent CO2, 18 mole percent oxygen, and 80.5 mole percent argon. Calculate the partial pressure of oxygen in the mixture if the total pressure is 745 torr, that's part A. Part B, if this atmosphere is held in a 120 liter space at 295 Kelvin, how many moles of oxygen? So earlier, I think it was Isvari. Yeah, so Isvari asked, what if you're not given the mole fraction? So in this case, we were given the mole percent. So mole percent, if you remember back to chapter 2 where we talked about percent abundance and fractional abundance, this is that same thing. So we're going to be able to convert the mole percents to fractional abundance by just dividing by 100, and then we can use that information. So for part A, we want to find my notes. So for part A, we know that the mole percent of oxygen is 18.0%, 18.0 mole percent. So we know that the fractional abundance of O2 is 0.18. And we know that because we just want to convert this to a fraction. So now we know chi1. And so we also know the total pressure. So P of O2 is equal to chi of O2 times P total. So we're going to take our 0.18 and multiply that by 745. And that gives us 134 torr. So for part A, we took our mole percent and then converted that into the P of the pressure of the oxygen by multiplying the mole fraction times the total pressure. So that gave us the partial pressure. So that's part A. So if this atmosphere is to be held in a 121, so Alice asks, do you not need to convert this into atmospheres? It doesn't ask you to do that. You could, and unless it's specified, and any question that I write would totally specify. Yes, so the 3 sig figs comes from both the 18.0 mole percent and the 745 torr. So here, this should have a 0 here, but I forgot it. So you don't have to convert it into atmospheres unless it asks. So in part B, it asks, is the atmospheres to be held in a 121 liter space at 295? How many moles of O2 are needed? So we can use this equation. N of O2 equals PV over RT. And so in this case, I am going to convert this to atmosphere, so I can use the R value I like. 760 torr in 1 atmosphere gives us 0.176 atmospheres. So we now have a pressure of 0.176, and our volume is 121 liters divided by 0.08206. And the temperature is 295 Kelvin. So we can plug that in and determine that we would get 0.880 moles and die. So sorry about that. That was awkward. If you have questions about this, you can look at it. I'm not leaving. The sig figs here is 3 also because of the problem. You could go back and do the same calculation for both the argon and the CO2. There are a few more slides in the slide deck. Those are kind of, I don't call them fun questions. That is not on the final. It is not on the exam. It is not on anything. It is not an Alex. You don't need to look at it. Partial pressures is the last thing that's on the exam. So we can definitely, this will be on the final. It will be just like this. So what other questions do we have? Or do we have any questions? If you guys need anything, please send me an email. I miss you guys so much. Someday when we're back at UNF, feel free to come by the office, stop in, say hi. I miss you guys. You guys are amazing. Stay safe. Good luck on the final. If you need anything, don't forget I have office hours this weekend. And I will have some on Monday. If you have questions, you can hit Megan up. You can hit me up. So I know this feels so sad, but Lily and I miss you guys. So keep in touch, send me emails, and we will see you soon. You guys are amazing. Have a fantastic rest of your day. And email me if you have issues. Oh, that is so Haroon, that's an A for part A of the problem. Good question. Well, that was a weird screenshot noise. I miss you guys. Y'all have a fantastic day. Stop into office hours or send me an email if you need anything. Bye, guys.